This is tutorial 3 and we will cover chapter 5. Chapter 5 is a survey of probability concepts. The relationship between probability theory and statistics will be very clear in the next chapter. We use a sample to estimate the properties of a population, and in the end this is just an estimate. So using ideas from probability, we can measure the reliability of the results. How reliable are the results obtained from a sample can be measured using probability. We will cover the following. First, define what probability means. So we define the terms of probability, what is an experiment, an event, and outcome. Then we will see how we can calculate probabilities, assign probabilities using several methods: classical, empirical, and subjective approach. Next, number 3, we will calculate probabilities using the rules of addition. Number 4, we will calculate probabilities using the rules of multiplication. Number 5, we will compute probabilities using contingency table. We saw an example of contingency table at the end of last tutorial. Now we will see how we can use them to calculate probabilities. Number 6 is not covered. 7, determine the number of outcomes using principle of counting. Turns out in many probability experiments, to calculate probability we do counting, and we do some counting, but the last outcome will be to learn a few rules about counting. First of all, the definition of probability. Probability is a value between 0 and 1 inclusive, meaning it can be 0, it can be 1, that represent the likelihood a particular event happens. So we're interested in particular experiment. Experiment has known outcomes. We want to measure the likelihood an event might happen. We will see that this will be a number between 0 and 1. The closer to 1 the probability, the more likely the event will occur. The closer to 0, the less likely the event will occur. We will start by a chart that gives us different possibility outcomes and probabilities that you might assign to it. We said a probability of 0, meaning it will not happen. The likelihood is very small. On the other hand, a probability of 1 or close to 1, that means the event is sure to happen. An example of probability with 0, an event with 0 probability, is the probability that our sun will disappear this year. You can assign a probability of 0 for this outcome. The second probability, the chance Slowpoke will win the Kentucky Derby. The Kentucky Derby is a famous horse race in Kentucky, and that's the name of a horse. Horses who participate in races, there's odds because money is gambling here. People bet money on horses. Normally the odds of a particular horse winning a race is known. The probability of this particular horse winning the Kentucky Derby is 0.20. Next probability, the chance of a head in a single toss of coin. Well, tossing a coin is one of the probability experiments we look at. There is only 2 outcomes: either you get a head or you get a tail, and we assume they are getting a head. This outcome is equally likely as getting a tail, so the probability of getting a head in a single toss of coin is equal to 0.50. Here is the next one, the chance of an increase in the federal taxes. Someone estimated that to be 0.70. Sometimes probability is reported as a percentage. يعني 0.70 is equivalent to 70% chance that there will be an increase in the federal taxes. Here is an event that is sure to happen, يعني guaranteed to happen, is chance of rain in Florida this year. Florida is known to be a state that gets a lot of rain every year. For the chance of having rain this year in Florida is near to 1 or equal to 1. Now we have a formal definition for an experiment. An experiment is a process that leads to the occurrence of one and only one of several possible results. The simplest experiment we already mentioned, if you toss a coin, there is only two possible outcomes. You either get a head or you get a tail. We will look at many experiments and see how to calculate probabilities for different outcomes or results. An outcome is a particular result of an experiment. For example, in the experiment of tossing a coin, getting a head is a particular result of the experiment. An event is a collection of one or more outcomes of an experiment, and we will have an example of that. Here an event may contain more than one outcome of the experiment. The one experiment that is used a lot in probability is rolling a die. A die, of course, is a cube with the cube has 6 sides. Each side has a number, from 1 to 6, using dots. The numbers 1 through 6 are present on each side. When you roll a die and look at the side that's showing up, it can the possible outcomes that you observe a 1 or a 2 or a 3 or a 4 or a 5 or a 6. Each one of these is a possible outcome. An example of an event: observe an even number. Observe an even number. This is an outcome that has an event that has 3 outcomes. You get an even number if you get the number 2 or 4 or 6. So here is an event that has 3 different outcomes. Observe a number greater than 4, and that will be 2 numbers, either 5 or 6. Choose a number, the number 3 or less. All of these are a collection of more than one outcome. These are called events. Here is another example. You can think of an experiment. Count the number of members of the board of directors of Fortune 500 companies who are over 60 years of age. You have 500 people here. Here the outcomes you're looking at, you are counting the number of people who are over 60 years of age. There could be none of them over 60, which is 0, or 1 is over 60, or 2 over 60, or up to the number of people in that group. Each one of these is a possible outcome of that experiment. Here is an example of an event. What is the probability that 13 of that group are over 60? That's an event that contains many outcomes. There could be 13, 14, 15, up to the number of people in that group. Here's another event. What is the possibility that you get fewer than 20 are over 60? All of these are examples of events. An event may contain more than one outcome. For the starting point is an experiment. The experiment has several possible outcomes. One thing that we know, if you have an experiment, you need to know all possible outcomes. The set of all possible outcomes is called the sample space. يعني for any experiments we work with, we like to see or calculate the probability of an outcome occurring or the probability of an event occurring. There is more than one approach. The one that we will look at is the classical definition of probability. This applies only when you have n equally likely outcomes to an experiment. So that's important, and to be able to use the classical definition of probability, you assume that every outcome of the experiment have the same chance of occurring. And for example, with the probability of tossing a coin, we said the probability of getting ahead is 1/2. And that's because the probability of getting ahead is equal to the probability of getting a tail. Here you calculate the probability, it's 1 divided by 2, which is the number of outcomes. That's how you calculate probability using the classical method. And that's, again, it is important to assume each outcome has the same chance. All the outcomes are equally likely to occur. The probability of an event, an event may contain more than one outcome. Count the number of favorable outcomes, divide by the total number of possible outcomes. The total number of possible outcomes is how many outcomes is in the sample space. Here are more definitions. Mutually exclusive, we have seen this, those terms used before. A mutually exclusive means the occurrence of one event means that none of the other events can occur at the same time. And again, going back to the experiments of heads or tail, if you conduct the experiment and get it head, then that's it. That's the event that will occur. The other event will not have occurred. The occurrence of one event means that none of the other events can occur at the same time. Collectively exhaustive, at least one of the events must occur when an experiment is conducted. You already know all the possible outcomes, so you assume when you conduct the experiment, one of the events occur when the experiment is conducted. Here's again the dice. It has 6, it's a cube, so it has 6 equal sides. They have different numbers represented by dot or spot, 1, 2, 3, 4, 5, 6. And this experiment is used a lot in probability theory. The next type of probability is called the empirical probability, and that in fact depends on actual data. You are interested in events with data, then the empirical in this case is you take the number of times the event did happen divided by the number of outcomes. But here your calculation is based on actual data, and we will see examples of that. Here is a definition of empirical probability. The probability of an event happening is the fraction of the time similar events happened in the past. What's the relationship between empirical probability and classical probability? This is covered by the law of large numbers. Over a large number of trials, the empirical probability of an event will approach its true probability. For example, tossing the coin once, the theoretical probability using the classical method is 1/2, because you have 2 equally likely outcomes to occur. In the case, if you want to use the law of large numbers, that means if I toss the coin a large number of times, let's say 1,000 times, I will see in the fraction where I get ahead will be very close to 1/2. The empirical probability, the probability based on actual data, if you repeat the experiment a large number of times, will be close to its true probability, in this case the theoretical probability, or the probability using the classical definition. Here is an example of empirical probability, and this is based on actual data. Probability of a successful flight is the number of successful flights divided by the total number of flights. طبعا airlines keep records of their flights. A flight is successful if it actually is completed. Sometimes for one reason or another, maybe for mechanical problems or any other reason, a flight is not successful, meaning it's cancelled. These records are kept. For this example, the airline company records show out of 123 flights in a given period, 121 were successful. Then the probability of a successful flight is equal the number of successful flights, which is 121, divided by 123 equals 0.98. Then this is a number close to 1, so the probability of a successful flight is very high. It's near certain that you will have a successful flight. The third type is the subjective probability. The subjective concept of probability is the likelihood or the probability of a particular event happening that is assigned by an individual based on whatever information is available. Normally people who assign that kind of probabilities are people who are experts, based on the information you have, based on past occurrences, you can predict how likely an event will occur. Maybe we gave an example of in the beginning of different outcomes. We said that the probability of an increase in federal tax is 70%. Now, the people who make that type of prediction are experts in economy, and based on the information available to them, and based on previous results, they expect in the taxes will be increased. The probability of an increase in federal tax is 70%. So that type of probability then is called subjective probability, and it is based on whatever information is available. Here is more examples of subjective probability. Estimating the likelihood the New England Patriots will be in the Super Bowl next year. The New England Patriots is a football team in the United States. Every team, the Super Bowl is the highest tournament in football. So you can estimate for each team based on their performances. This is information that you have at hand, based on the players they have, based on their coaching staff. You can predict or estimate how likely that this team will make it to the Super Bowl. But this is another example of subjective probability. Another example, estimating the likelihood the U.S. budget deficit will be reduced by half in the next 10 years. And again, that type of prediction is normally based on information that's available at the time. You can assign a probability based on information that is available at the time. Here is a chart from your book that summarizes the different approaches to probability. The objective type, there is two types. The classical probability, which is based on equally likely outcomes. The other type is empirical probability, which is based on data, based on relative frequency. Relative frequency, that means you have data, and based on that you can calculate relative frequency of outcomes, which will give you the probability. The other one is the one we just covered, is the subjective, and that's based on available information. Now, as we defined before, an event may contain more than outcome. Sometimes we calculate in the end, an event is simply a subset of the sample space. The sample space is all possible outcomes. An event is simply a subset of the sample space. For many things we know about sets, we can use to calculate probabilities for events, or the union of events, or the intersection of events. Many of the rules we know about sets can be used to calculate probabilities for events. So we will look at several rules. First, the rules of addition. This refers to the probability that any of two or more events can occur. Yani, for example, you have two events, A and B. So you may calculate the probability. What is the probability that either one of these will occur? Yani either A will occur or B will occur. This is a situation where you use the rule of addition. And that's here the rule depends how do you calculate the probability of A or B. Here is the rule. This is in the special case, if A and B, remember these are all sets, so if A and B are mutually exclusive, meaning they have nothing in common, then the probability of A or B occurring is equal to the probability of A plus the probability of B. And this is for the case where they have nothing in common, they're mutually exclusive. We have another formula that will cover the case where they might have something in common, and it is based on what we know about sets. After all, you are counting, and the probability of an event is the number of outcomes in the event divided by the total number of outcomes. Counting here is involved. We will see a rule that covers the probability of A or B occurring in case where A and B are not mutually exclusive. Here is an example that explains the idea of the union of events, or the probability of A or B occurring. So here we have a machine, a factory that fills bags with a mixture of vegetables. This factory fills plastic bags with the mixtures of beans, broccoli, and other vegetables. Most bags contain the correct weight. There's always a target weight, and since machines do the work, it is not always exactly, the machine does not always fill the bags with exactly the correct amount. So we're interested here in the bags having the correct weight. Because of variations in the size of beans and other vegetables, a package might be underweight or overweight, and it could be exactly right or very close to being exactly right. A check of 4,000 packages filled the past month revealed. So this is actual data. This is the data from the factory. So out of 4,000 packages that were checked, here are the table summarizes the outcome. Here the event A is the probability of underweight. We found 100 packages. This is 100 packages out of 4,000 packages. So the probability of getting a bag that's underweight is 100 divided by 4,000, or 0.025. Event B is the probability of getting a bag that's satisfactory, meaning it's very close to the exact weight. Most of the bags are like that. There was 3,600 bags that were satisfactory. For here the probability then of getting a bag that is satisfactory will be 3,600 divided by 4,000, or 0.90. The third possibility is that the bag would be overweight. This is event C. We found 300 bags that are overweight. The probability will be 300. So the probability of getting a bag that's overweight is 300 divided by 4,000, or 0.075. The total of probabilities is always equal to 1. And here the events that we have, A, B, and C. Clearly B, the probability of getting a satisfactory bag, or a bag that have satisfactory weight, has the highest probability, almost 90% chance of getting a bag that has satisfactory weight, or the probability of event B has the highest probability. Here is now an example of using the union of two events or outcomes. What is the probability that a particular package will be either underweight or overweight? Well, this is the probability of A or C, يعني either underweight or overweight. These two events are mutually exclusive. They have nothing in common. So according to our law of addition, this is the probability of A plus the probability of C. This is equal to 0.10. This is the probability of either the bag is underweight or the bag is overweight. So we add the two probabilities. Now the complement rule is used to determine the probability of an event happening in terms of the probability of the complement. You subtract the probability of an event not happening. طبعا it is always the case if we take any event, the event not happening is just the complement. It's always the case that the probability of an event plus the probability of its complement, yani the probability of the event not happening, this sum is always 1. So one way to calculate the probability of an event is take the probability of the event not happening, or the complement, and subtract it from 1. So here is the complement rule. The probability of A is equal to 1 minus the probability of the complement. In our example here, the event that we calculated, which is the probability of underweight or overweight, we added the probability and we got 0.1. The other way to do it is to see the probability of the complement. Here the complement of underweight or overweight, that the bag would have satisfactory weight, which is B. But then the probability of A or C is equal to the probability of the complement of B. The probability of the complement of B is 1 minus the probability of B. 1 minus 0.90 is equal to 0.1. يعني think of we're interested in the probability of A or C, so look at the complement. What's the complement of A or C? That the complement in this case, that you get a satisfactory weight, which is B. Then the probability of A or C can be calculated as 1 minus the probability of B, which in this case it is 0.1. And طبعا as you expect, you get the same probability as we did before. We started by the rule of addition, which covered the case if the two events are mutually exclusive, meaning they have nothing in common. Here is now the general rule of addition. It covers a case where the two events might have something in common. And these rules again follows from rules of sets based on counting. This is the general rule of addition. It's used when the events are not mutually exclusive. For the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. In terms of set, this is the number of outcomes in the union equal to the number of outcomes in A plus the number of outcomes of B minus the number of outcomes in the intersection, because these outcomes are counted twice because there is an overlap. So if you add the number of elements of A plus the number of elements of B, you have counted the intersection twice. So you subtract the number of outcomes in the intersection, and that would give you the general rule of addition. The probability of A or B, which you can think of it as the union of A and B, is equal to the probability of A plus the probability of B minus the probability of the intersection. Here's an example of applying the general rule of addition. We have a sample of 200 tourists in Florida. Shows 120 went to Disney. That's Disneyland. These are all tourist attractions. Out of 200 tourists, 120 went to Disneyland, 100 went to Busch Gardens, 60 visited both places. That's the intersection now. Here we are given, or we can calculate the probability of Disney, since 120 visited out of 200. For the probability of a tourist, if we select a tourist at random, the probability that he visited Disney is 120 divided by 200, or 0.60. The probability that a tourist selected at random visited Busch Gardens is equal to 100 divided by 200, and now we know 100 people went to Busch Gardens, which is 0.50. The probability that the tourist visited both places, Disney and Busch, is 60 divided by 200, and now we know 60 people visited both places. Now, if I want to calculate the probability that a tourist visited either Disney or Busch, if I take the probability of Disney plus the probability of Busch minus the probability of Disney and Busch, which is the intersection. This is 0.60 plus 0.50 minus the probability of the intersection, which is 0.30. The result should be 0.80. This is a probability that a tourist has visited either Disney or Busch. The next rule we'll look at is called the rule of multiplication. The rules of multiplication are applied when two or more events occur simultaneously. And now you're looking at the intersection. What is the probability of two events occurring at the same time? The special rule of multiplication refers to events that are independent. We will see if the two events are independent, we can calculate the probability of the intersection, and both events happening simultaneously by multiplying the probability. So what is the definition of independence? The occurrence of one event has no effect on the probability of the occurrence of another event. Again, the occurrence of one event has no effect on the probability of the occurrence of another event. We will see if two events are independent, they satisfy this condition, then that gives us a special rule of multiplication. The probability of A and B is equal to the probability of A times the probability of B. This is called special rule of multiplication because we require that the two events are independent. The general rule, which we'll cover later, will cover the case where the two events may not be independent. But at least for now, if I know two events A and B are independent, then the probability of A and B occurring is the product. It's equal to the probability of A times the probability of B. Here is an example of using the special rule of multiplication. A survey by the American Automobile Association, or AAA, revealed that 60% of its members made airline reservations. This is an automobile association, so it's people who travel using cars mostly, but they also fly. Their survey, they call their members and ask them. Anyway, they found out that 60% of their members made airline reservations last year. Suppose you pick two members select them randomly. Select two members randomly. What is the probability that both made airline reservation last year? The two people are selected have nothing to do with each other. So the probability that one of them making a reservation have nothing to do with the probability that the other person made the reservation. So these two events are independent. R1 is the event that the first person made the reservation. R2 is the event that the second person made the reservation. R1 and R2 are independent. The probability of R1 and R2, both persons made reservations last year, is the product of the probabilities. Probability of R1 times the probability of R2. Each one of them is equal to 0.60, so multiply the two probabilities, you will get 0.36. This is a probability that both persons selected made airline reservations. The next rule, it's the same, the rule of multiplication, in the case where the two events may not be independent. And that will give rise to an important concept in probability, and that is the concept of conditional probability. The general rule of multiplication refers to events that are not independent. We will calculate the probability that two events occur at the same time, given that they may not be independent. This is called conditional probability, is the likelihood of an event will happen given that another event has already happened. But that's the definition. Conditional probability is the probability of a particular event occurring given that another event has occurred. طبعا we will look at the formula for that. This just to explain the concept of conditional probability. Here is another example. We know that when you roll a die, the possible outcomes are any number 1, 2, up to 6. There's 6 possible outcomes. So you may get, you may ask, what is the probability when you roll a die? What's the probability of getting the number 2? In this case, it will be 1 out of 6, 1 over 6. Conditional probability here, let's say, is if we want to calculate what is the probability that you get the number 2, given that the outcome will be even. So by knowing that the outcome will be even, there is only 2 possible outcomes, 2, 4, and 6. The probability now becomes 1 over 3. The condition, when you calculate probability in this case, there's a condition which will limit the sample space. It will limit the possible outcomes, and therefore you get a different probability. If you already know the outcome will be even, the probability of getting a 2 now will be 1 over 3. But that's the idea of conditional probability. You calculate the probability of an event given that another event has already occurred. For the general rule of multiplication, the probability of A and B is equal to the probability of A times the probability of B given A. The probability of both events are occurring is equal to the probability of A times the probability of B given A, the probability of event B given that A has occurred. طبعا this probability of B, that then you draw a line, then A, this is a conditional probability. This is how it's certain. The probability of B given A, this is a conditional probability that the event B occurs given that A has already occurred. طبعا this same formula, actually you can write a formula to calculate conditional probability. From this same rule of multiplication, what is the probability of B given A? What is the conditional probability of B given A? It is equal to the probability of A and B divided by the probability of the condition, probability of A. Let's see how the general rule of multiplication is used, and طبعا that will involve conditional probability. The problem here, a golfer has 12 golf shirts in his closet. 9 of these shirts are white and the others are blue, 3 will be blue. 9 white, 3 blue. He gets dressed in the dark, so he just grabs the shirt and puts it on. He doesn't know which color he has selected. He just grabs the shirt and puts it on. He plays golf 2 days in a row and does not return the shirts to the closet. What is the probability that both shirts are white? We will see in the two events that we'll be calculating are not independent, so conditional probability is selected. First of all, W1 means that he selects a white shirt in the first day. W2 is the event that he selects a white shirt in the second day. For W1 and W2, يعني for both of them to occur, that means he selected a white shirt in the first day and a white shirt in the second day. And that's what we want to know, the probability that both shirts are white. طبعا these events are not independent. Here the probability of W1 and W2 would equal to the probability of W1, and he selects a white shirt in the first day, times the probability of W2, and he selects a white shirt in the second day, given that he selected a white shirt in the first day. طبعا the probability of W1 that he would select a white shirt, remember there was 9 white shirts out of the 12, so the probability will be 9 over 12. What is the conditional probability in this case? What is the probability that he selects a white shirt, given that's in the second day, given that he selected a white shirt in the first day? If he selected a white shirt in the first day, there's only 11 shirts left, and only 8 of them are white. So this probability now is 8 out of 11. Again, the probability that he selects a white shirt in the second day, given that he selected a white shirt in the first day. If he selected a white shirt in the first day, there's only 8 white shirts left out of how many? Out of 11. But this probability will be 8 divided by 11. The product of the two probability will be 0.55. This is a probability that he would select a white shirt in both days. Next, we would like to see how to use contingency tables to calculate probabilities. We have already seen an example of a contingency table, and here is the definition again. A contingency table is a table used to classify sample observations according to 2 or more identifiable categories or classes. We'll look at another example of a contingency table, and in the next slide we will see how to use contingency tables to calculate probabilities. In particular, we'll see how to calculate conditional probabilities. For this table, we have 150 adults were asked their gender and the number of Facebook accounts they used. So there is the two categories. We are interested in knowing the gender, male or female, and the number of Facebook accounts they used. And the sample here has 50 adults. The following table summarizes the results. طبعا you have the gender here is either men or women. The number of Facebook accounts is either 0, 1, or 2 or more. There's 3 categories. In the group that has no Facebook accounts, 0 Facebook accounts, there is 20 men, 40 women, for a total of 60. The group that has 1 account, there's 40 men, 30 women, for a total of 70. The third group, people who have 2 or more accounts, there's 10 men, 10 women, for a total of 20. طبعا the sum of the first column, men, is 70. That means we have 70 men in the group. The sum for women is 80, so we have 80 women in the group. طبعا 70 plus 80 is 150, which is the number of people in the sample. Also, if you add up the numbers from each group, the sum will be 150. So here is another example of a contingency table, and we will see in the next slide actually, we will look at another example of a contingency table and use it to calculate probabilities. For this example, the information we have here, last month the National Association of Theater Managers conducted a survey of 500 randomly selected adults. So your sample has 500 adults. The survey asked respondents their age and the number of times they saw a movie in a theater. These are the two categories: the age and the number of times they saw a movie in a theater. And here are the results. For the age category, there is three groups: people who are less than 30 years old, people who are between 30 and 60 years old, and the third group has 60, people are 60 years of age or older. For the number of movies, by the way, it may be easier to consider these to be event. Here the chances of selecting a person, or the event that you select a person who's under 30 years old, is B1. The group of people between 30 and 60 is B2, and 60 or older is B3. For the number of movies watched, there's 0, which we will call event A1. People who watched between 1 and 2 movies, that's A2. 3, 4, or 5 is A3. 6 or more is A4. No one, we're just labeling these groups because it will make it easy to use the table. The two categories are age, and here is the three groups. The number of movies watched, there's actually 4 different groups: 0, 1 or 2, 3, 4 or 5, and then 6 or more. If you look at B1, this is the people who are under 30 years old. 15 of them watched 0 movie, 25 watched 1 or 2 movies, 55 watched 3, 4 or 5, 5 watched 6 or more. And each group, you have the number in each group, the number of people who watched 0 movie or 1 or 2 or any one of those classes for number of movies. The total for each column, for example, the first column gives you 100. That's how many people who are under 30 years old, under 30 years age. In the second group, people who are between 30 and 60, there's 225. In the group of people who are 60 or older, there is 175 people. The sum of the row here should be 500. Then the total of people in the sample is 500. If you add up the different groups, the groups that are classified according to the number of movies that I watched, if you add these numbers in this column, you will also get 500. Here is another example of a contingency table. We will use this table to calculate several probabilities, including conditional probability. Okay, the first probability we want to count is the probability of selecting an adult who attended 6 or more movies per month. This is group A4 or event A4. The people who watched 6 or more movies, there are 50 people who watched 6 or more movies. Out of how many? Out of 500. So selecting a person from that group at random, the probability that he attended 6 or more movies is equal to 50 over 500, or 0.1. The second probability we want to calculate, the probability of selecting an adult who attended 2 or fewer movies per month, where there are 2 or fewer means 2 or 1 or 0. For the number of people who watch 2 or fewer are the people in the second group, 200, plus 75, which are people who watch 0 movie. For the probability of selecting an adult who attended 2 or fewer is the sum of these two groups, 200 plus 75. That gives you how many people in the sample watched 2 or fewer movies. Divided by the number of people in the sample, 275 divided by 500 is equal to 0.55. Next, we want to calculate other probabilities. We want to see the probability of selecting an adult who attended 6 or more movies per month, from the group A4, or is 60 years of age or older. This is now this is a union of two events. Either the event in the person attended 6 or more movies per month occurs, or that you are selecting a person who is 60 years of age or older. So the rule is take the probability of the first event, which is that you select a person who attended 6 or more movies. Well, we already said there's 50 people, so this is 50 over 500, plus the probability that the person is 60 years or older. Well, there is 175 people who are in that group who are 60 years or older, divided by 500, minus the intersection. Now the intersection means a person that is 60 years or older and watched 6 or more movies. So it's actually the intersection of this row, which is people who watched 6 or more movies, and this column, which is people who are 60 years or older. Well, there's 30 people in the intersection. That means you have 30 people who are both. They are 60 years old or older, and at the same time they watch 6 or more movies. For the intersection then is 30, so you subtract 30 over 500. This is just applying the general rule of sum, and the result should be 0.39. The next probability, we want to select the probability of an adult who attended 6 or more movies per month, given the condition that the person is 60 years of age or older. Now, with conditional probability, it's easy to use contingency table to calculate conditional probability. Since the condition tells you that the person is 60 years of age or older, you only look at this column, the third column. And now your sample space is limited to those people who are 60 years or older. How many watched 30 or more movies? There's 30 out of this group, which is 175. Again, because of the condition, we know that the person is 60 years or older. That means your sample space is now limited to this group, the people who are 60 or older, which there's 175 people. There is 30 in that group that watched 6 or more movies. For the probability in the person selected have attended 6 or more movies, given that he is over 60, would be 30 divided by the total number in that group, which is 175. 30 over 175 is equal to 0.17. One more probability we want to calculate the probability of selecting an adult who attended 6 or more movies, from group A4, and is 60 years of age or older. Anytime you see and, this is the intersection of two groups. This is the intersection of the group of people who watched 6 or more movies with the people who are 60 years or older. There are 30 people, as we counted before, that are both 60 years of age or older and watched 6 movies. But this time around, this is a probability of selecting one of those people out of how many? Out of 500. Then the probability will be 30 over 500, or 0.06. Here is another contingency table. This time we want to look at the idea of tree diagram. Tree diagram is useful to calculate probabilities, especially conditional probability. A tree diagram is a visual that is helpful in organizing and calculating probabilities for problems with several stages. Each stage of the problem is represented by a branch of the tree, as we will see in the next slide. And you label the branches with the probability, and you will see it will summarize many of the probabilities, and also you can use it to calculate conditional probabilities. But here is this is the same table of the sample of 500 people, and they're classified according to their ages and how many movies they have seen. This information now can be summarized in a tree diagram, as we will see in the next slide. Here is, طبعا we can't check all the details, but let's look at some of the branches. The first category is the age, so we know that there are 3 ages or 3 groups: 30 years or younger, 30 to 60, and over 60 years old. For this branch of 30 years old or younger, we know that there is 100 people in that group. The probability of selecting one from that group is 100 over 500, or 0.20, and you can write this on this branch. For the group that are 30 to 60 years old, there's 225, where the probability of selecting one in that group is 225 divided by 500, or 0.45. The probability for the third group is calculated similarly. The probability of selecting a person who is 60 years old or older would be 175 over 500, which is 0.35. Each branch here gives you the different group according to the category of age. Now for each one of these groups, there is now 4 possibilities as far as the number of movies were watched. So you look at each branch here, there's 4 different possibilities. Either the person watched 0 movie, or 1 or 2 movies, 3 or 4 or 5 movies, and the 4th category is 6 or more movies. And that you have to do for each branch, for each group in the age group. But you can also calculate probabilities in this case. In the group of 30 years old or younger, there was 15 that watched 0 movies, so the probability is 15 over 100, or 0.15. In this same group, there's 25 that watched 1 or 2 movies, so the probability of selecting 1 or 2, a person that watched 1 or 2 movies from that group is 25 over 100. طبعا you can do this for every possibilities or every branch in that group, and the same is done for the second age group and the third age group. But here is how you can use the tree diagram for conditional probability. For example, if you want to calculate the probability that a person watched 1 or 2 movies, given that he's 30 years of age or younger, here you have to multiply the probabilities. You multiply the probability that the person is 30 years old or younger, which you calculated to be 0.20, times the probability that he watched, given that condition, the probability that he watched 1 or 2 movies is 0.25. For the product of these 2 probabilities, 100 over 500 times 25 over 100 gives you 0.05. This probability here is the probability that the person watched 1 or 2 movies, given that he's 30 years old or younger. You can think of the first branch as a condition, and then you can calculate the probability of selecting a person according to now the number of movies that were watched. This is rather a big tree because there's a lot of categories. In many problems, the possibilities are less, so you have a more compact tree that you can work with. But you can see a lot of probabilities are calculated, and also conditional probabilities can be calculated. At least some of the conditional probabilities can be calculated using the tree diagram. We will see more examples of tree diagrams. Here is a rule also. It's actually a rule for counting, and rules of counting are important because we have seen in sometimes calculating probabilities amount to counting how many outcomes are in the event. This is considered to be a rule of counting, and طبعا it can be used for calculating probabilities. This is called the multiplication formula. The multiplication formula states that if there are n ways of doing one thing and m ways of doing another thing, then there are m times n ways of doing both. يعني again, there's n ways of doing the first thing, m ways of doing the second thing, so the number of ways you can do them together is m times n, as this example will show. طبعا the formula, the total number of arrangements is m times n, where m is the number of arrangements for the first way and n is the number of arrangements for the second way. Here is an example that would explain this. You have an automobile dealer wants to advertise for the 29,999, يعني that's the price of a car. But here are the choices. يعني there are several choices here. You can buy a convertible, a two-door, or a four-door model. So there's three models that you can select from. Either a convertible, or a two-door, or a four-door model. Now for each of these choices you can select يعني the style of wheels. You can choose either a wire wheel or a solid wheel cover. So there is three ways to select the model. There is two ways to select the wheel. So how many different vehicles can the dealer offer? يعني how many choices do you have? Well, there are three different ways that you can select the model. For each one of these ways, there is two ways to select the style of wheel, where the number of ways is 3 times 2, which is equal to 6. In fact, here are the 6 choices. طبعا you have 3 different choices for the model. For each choice of the model, there is 2 different choices for the wheels. So there is altogether 3 times 2, or equal to 6 different ways you can select the car. Next, we will end this chapter by doing 2 more formulas for counting. The first one is called the permutation formula. Permutation, يعني we'll see the definition. This is a counting formula that we use to determine the total number of outcomes. A permutation is any arrangements of R objects selected from a single group of n possible objects. Here you start with a set of n objects and you want to select R of these objects. طبعا R would be less than or equal to n. You can select all of them and or select يعني a smaller number. For example, you may start with 10 different objects and you want to select only 3. So the question is how many arrangements, how many ways you can select the objects. It's important when you see a permutation, this is an arrangement, so the order matters. يعني the order of the arrangement matters. Before we look at the formula, suppose you want to select a word consisting of 3 letters out of the first 10 letters of the alphabet. For here, one selection may be A, B, C, or it could be BAC. These are 2 different selections. Anytime you're looking at an arrangement, here order does matter. A permutation or an arrangement, the order is important, but we will see now a formula how to select and how to arrange, or the number of arrangements, the number of permutations of R objects selected from n possible objects. Here طبعا R would be less than or equal to n. Here is the permutation formula, and here is the symbol we use. Start with n, the number of possible objects, P for permutation, capital P, and R is the number of objects you are selecting. NPR, يعني the number of arrangements or permutations of R objects selected from n possible objects. The rule says you take n factorial divided by n minus r factorial. يعني the first number factorial divided by the difference factorial. N factorial, you should know what that means. يعني this is a number you obtain by multiplying n times n minus 1 times n minus 2 until you get to 1. And for example, 5 factorial is 5 times 4 times 3 times 2 times 1. And all scientific calculators should have this feature, and you can calculate n factorial for any positive integer n. So here's the rule one more time. NPR, this is a number of R permutations selected from n possible objects. It is n factorial divided by the difference n minus R factorial. طبعا R, as we said, could be any number up to n. R is less than or equal to n. So here is an example. There are 3 electronic parts to be assembled. N is equal to 3. Now here you are using all the objects because you are arranging the 3 electronic parts. So here n equal R equal 3. You're arranging all the objects that you start with. N is equal to 3. All 3 to be inserted into a plug-in component. For here, the number of permutations, the number of ways you can arrange the 3 electronic parts is just 3p3. This is the number of permutations of 3 objects out of the 3. This is the first number factorial, 3 factorial, times the difference, 3 minus 3 factorial. 3 factorial is 3 times 2 times 1, which is 6. 0 factorial is just 1. There's only one way to arrange 0 elements. 0 factorial is equal to 1. This is equal to 6. So there are 6 ways that you can arrange the 3 parts. In fact, you can label them. If you label the 3 parts A, B, C, then here are the 6 different ways you can arrange them. A, B, C, B, A, C, C, A, B, A, C, B, BCA, and CBA. These are 6 different arrangements of A, B, C. طبعا each letter here represents one of the parts. The second counting formula is when order is not important. But here you're still selecting R objects from N objects, but order is not important. These are called combinations. For the combination formula, this is another counting formula useful in determining the total number of outcomes. We use them for counting outcomes. A combination is an arrangement where order of the objects selected is not important. If you go back to our example of selecting ABC, for ABC is the same as CAB is the same as any other arrangement. Here order will not be important. So we will have problems where we are counting or selecting R objects from N objects where the order is not important. This is called combination, and here is the formula, how to count the number of combinations. This is a combination formula. This time we use capital C for combination, so it's N, C, R, or some books would say N choose R. The N choose R, or the number of R combinations out of N objects, is N factorial divided by R factorial times N minus R factorial, times the difference factorial. Let me say it again. This is N choose R, or the number of R combinations out of N objects. It is equal to N factorial divided by R factorial times N minus R factorial. Here is an example. The Grand 16 movie theater, that's the name of the theater, uses teams of 3 employees to work the concession stand each evening. There are 7 employees available to work. You have 7 people to select from, and you want to select 3 to work in the stand for each night. For here, the order of the 3 is not important. You are just selecting 3 people, and they will work together in any particular night. For 7 employees to select from, and you want to select 3. So this is 7 choose 3, or this is the number of combinations of 3 people, or the 3 combinations from 7. The formula says n factorial divided by r factorial times n minus r factorial. N is 7, so this is 7 factorial divided by 3 factorial times the difference, 7 minus 3 factorial. This is 7 factorial times 3 factorial times 4 factorial. طبعا for smaller values of n and r you can calculate it without a calculator, or طبعا you can always use a calculator to evaluate numbers. Using the calculator you can calculate any calculations that have factorial in it. The result of this calculation should be 35. So there's 35 different ways. You can select 3 employees out of the available 7 employees to work in the concession stand.